If you solve this, you should be good at any kind of bomb calorimetry problem on your midterm or final exam. So we'll jump through it. Oh, before I say that, I encourage you to pause it, work through this on your own, and then come back after and see how you did. Work through it with me. Okay, so a 1.1830 gram of benzoic acid, and we have an internal energy, change in internal energy of negative 26.434 kilojoules per gram, was burned in a bomb calorimeter, and the temperature rose from 23.660 degrees Celsius to 24.948 degrees Celsius. 3 decimal places is common in bomb calorimetry for temperature. And then in the same calorimeter, 1.0011 grams of sucrose was burned. Okay, so we have 2 experiments going on, and the temperature rose by 1.640 degrees Celsius. Okay, so we're asked to calculate the enthalpy of combustion. So enthalpy of combustion is the change in enthalpy of combustion at 298 Kelvin of sucrose. So we want to know it of this one right here. But we're okay. Now, one thing that's missing, and we need to make note of that, is that there's no heat capacity of the calorimeter given. We don't know what that is. So we can't really solve this problem, find out what the change in enthalpy of combustion is, without knowing what the heat capacity of the calorimeter is. That's why this first run is performed. And if you've done this in the lab, then you'll know that you always do a calibration run. So this first part here is performed in order to find out what Ccal is, what the heat capacity of the calorimeter is. So we're going to use, this is like the first one, and then this is like the second part here. So for the first experiment, we need to find out the heat capacity of the calorimeter. Now this is a bomb calorimetry problem going on. So we're going to set up, as usual, the heat transfer of the reaction plus the heat transfer to the calorimeter has to equal 0. Now the energy transferred is heat in the reaction. That's directly equal to the change in the internal energy because the volume is constant, right? I did this before, right? This is the first law of a closed system. Change in internal energy equals the energy transferred as heat plus the work. Since volume is constant, there's no work being done. Negative P delta V, right? Delta V, so delta V is 0, so there's no work. So the heat of the reaction is equal to the change in internal energy of the reaction, and the heat transfer to the calorimeter is equal to its heat capacity times the change in the temperature equals 0. Okay, so now we can find it. So because we have this change in the internal energy of the reaction, that's right here, negative 26.434 kilojoules per gram. But I'm going to solve for Ccal first. I'll solve for Ccal. Actually, I'll do 2 steps at once if that's okay. I'm going to transpose this term to the other side to make it negative. So this would be negative 434? Nope, 26.434. Negative 26.434 kilojoules per gram. And then we're going to divide it by the change in the temperature, which is, okay, so we should pull out the calculator. Probably don't need it if we think about it, but that's okay. The final temperature is 24.948, so T final minus T initial, 23.660. Don't need the 0, but that's okay. So the temperature change is 1.288. So 1.288 degrees Celsius. Now, before I calculate this, let's calculate it actually. You know what? Let's do it. Let's not do too many steps at once. Okay, so negative 26.434 divided by 1.288 is negative 20.52, negative 20.523, negative 20.523. Now look at these look at these units. Nothing cancels, right? This is kilojoules per gram degrees Celsius. And this is a calorimeter, so we don't want things in per gram degrees Celsius. And this is per gram of what? Well, this gram comes from here. And this gram, the unit comes from here, which is a property of the benzoic acid. So when 1 gram of benzoic acid combusts, we get its internal energy changes by negative 26.434 kilojoules. So this is per gram of benzoic acid. But we don't have 1 gram of benzoic acid in here that we're burning. We're not burning 1 gram, we're burning 1.1830 grams. So to get the heat capacity of the calorimeter, we need to consider these 1.1830 grams, not just the 1 gram, which is what's given to us here. And this is common. So what we're going to do is, rather than per gram, we're going to multiply this. So we're going to say Ccal, I'll say Ccal over here is per gram. And then this is our actual Ccal, is negative 20.523 kilojoules per gram degree Celsius. So if this is small, divided by, no, not divided by, we got to multiply it so our grams cancel. 1.1830 grams, so that our grams cancel out. That's fun. And we're left with kilojoules per degree Celsius. So we'll plug that into our calculator. Oh, I got the number right there. So negative 1.183 is negative 24.279. So negative 24.279 kilojoules per degree Celsius. Okay, awesome possum. So we did this first experiment, the calibration run, in order to get the heat capacity of the calorimeter. So that's number one. And now we'll look at the second experiment here to get the enthalpy of combustion of sucrose. So let's consider what's going on here. We're burning sucrose, blah, blah, blah. It's a bomb calorimeter. So what we're going to do is we're going to set up this. This is a variation of the first law of thermodynamics. So we'll just write it out again. Q reaction. Now this is the reaction of the sucrose, right? This first one is the benzoic acid. Benzoic acid. The second part is for the sucrose. So the heat transfer of the sucrose plus the Q of the calorimeter has to equal 0. Now, Q of the reaction, that's not the change in enthalpy. The Q equals delta H only for a constant pressure or coffee cup calorimeter. In a bomb calorimeter, Q is equal to the change in internal energy right here. So that's very, very important. You don't want to forget that, or everything's going to be wrong. Okay, so the Q of the calorimeter is Ccal times its change in temperature equals 0. Now, we're solving for the change in internal energy, but we want the enthalpy. We're going to use the definition of enthalpy, like in the previous problem. Enthalpy is defined as the internal energy plus the pressure times the volume. We're going to use this to convert, once we got the internal energy change, to the enthalpy change. But first we need to solve for the change in internal energy. So we'll do that. So the change in internal energy of the reaction is equal to negative Ccal, which is, oh, so Ccal, wait a second, why is Ccal negative? That doesn't make any sense. This is negative. This is, oh, this should be, no, this is fine. This Ccal, what did I do wrong here? This, oh, when I move this over, this should be positive. Okay, so this is negative, right? But I transpose this to the other side. Just see, this is what happens when I skip steps. This should be positive here, because this whole thing is, say, this whole equation is Ccal equals negative delta U divided by delta T. But delta U is negative, so we have negative delta U. Delta U is negative, so we have a negative and a negative to make, so we got to make it positive. Yeah. You know, I should have saw that when we saw that the calorimeter is negative. You can't have a negative heat capacity. That's not going to work. You put energy into the system and it gets colder. That doesn't really make too much sense. So it's got to be positive. Okay, so 24.279 negative. Now I am moving this over to the other side. So I am subtracting this term. So I do put a negative there. Negative 24. Oop, I'll make it blue. 24 point, what was it? 279. 279 kilojoules per degree Celsius times the change in temperature, which is, so they gave us the change. It rose by this value. So this is the change in temperature, 1.640, 1.640 degrees Celsius. Okay, so we'll plug it in. So I have this number, so I'm not going to clear my calculator. I'm just going to use that number again. 1.640, don't need the 0. Negative 39.818 818, I guess, negative 39.818, negative 39.818, and our degrees Celsius cancels out, so we're left with kilojoules. Kilojoules, okay, kilojoules. So this is kilojoules for this many grams of sucrose, right? And we want the enthalpy of combustion. Now, it doesn't say it here, and it should in the question to help you, but if it doesn't say it, this is really per mole. So this is usually in kilojoules per mole. And I guess in this question, the students just have to know that this is in kilojoules per mole. That's what you look up on tables. It's quoted in tables in kilojoules per mole. So that's what we're going to calculate it in. Now, unfortunately, we got the change in internal energy in kilojoules, and it's kilojoules for this many grams of sucrose. We want it per mole of sucrose. So, just like the previous question, we're going to calculate what it is per mole of sucrose. So we have negative 39.818 kilojoules, and that's for every 1.0011 grams, 0.011 grams of sucrose, and we want per mole. So we want grams to cancel out. We want moles downstairs in the denominator. For 1 mole of sucrose, it weighs 342.3 grams, 342.3 grams. So 342.3 grams. Oh, we might need another significant figure, but I could calculate it. We'll keep the 4 for it, just to we'll keep that down. We'll keep the 4 sig figs. Should be good. Okay, so that is, let's see. I got this number in the calculator, so I'm going to keep it there. 342.3 negative 13,629. 13,629.6. 13,629.6. So 13 negative 13. Oh, holy moly. Well, 13. There we go. 629. I lost count. 629.6. 629.6. And this is in kilojoules per mole. Kilojoules per mole. It's a pretty big number, but 1, 2, 1. Okay. Yeah, I think we're good. All right. So this is our change in internal energy per mole. But we want the change in enthalpy. So we're going to use this equation here. The change in enthalpy equals internal energy plus the pressure times the volume. So we're going to make some more room. And we'll start off with our definition of enthalpy as before. Enthalpy is defined as the pressure as the internal energy times plus the pressure times the volume. So the change in enthalpy is equal to the change in internal energy plus the change in the pressure times the volume. And we have this change in internal energy, but to get the change in the pressure times the volume, as with the last question, we need to resort to the ideal gas law. Now we're burning sucrose, and we're given this molecular formula. So C12H22O11, C12H22O11. So C12, oh, that's supposed to be a 12. There we go, C12H22O11 plus oxygen, because we're burning it in the presence of oxygen, gives us CO2 gas plus water gas. Okay, so what's happening here? We have 12 carbons in sucrose, so we're going to get 12 CO2s, and then we'll balance the hydrogens. We have 22 hydrogens, so we need 11 waters here. Oh, this should be a liquid. Should definitely be a liquid. So it produces water as a gas initially, because it's so exothermic, but after it cools down and we have heat transfer to the calorimeter, this is going to go into a liquid, and at 298 Kelvin, which is what we want the enthalpy of combustion for, at 298 Kelvin, water is a liquid predominantly. So like a little bit of vapor pressure, but it's a liquid. So we've got to have this as a liquid. Okay, so we balance the hydrogens, we need to balance the oxygens, 24 oxygens, so 35, 24 plus 11, so 35, 35 minus 11, oh, we're back to 24. So we have 24, and so this has to be a 12 here. This has to be a 12. 24, yeah. Okay, Cool beans. So I can kind of see where this is going, but we'll go through the steps just in case you're not given this exact problem. Now, the change in the pressure, because this is bomb calorimetry, so the volume doesn't change. This term only depends on the change in the pressure times whatever the volume might be, and the change in pressure is due to the gas because there's no pressure exerted by the solid or the liquid. So it's just the gas. So we can use the ideal gas law, PV equals nRT, so that the change in the pressure times the volume is equal to the change in the number of moles times gas constant times the temperature. And this change in moles is going to be, that's final minus initial, which is products minus reactants of moles, or not of moles, of gas times the gas constant and times the temperature. And this term here, this is a very important point. This term is the change in internal energy that we measured from the calorimeter, right? This is measured from the calorimeter. This term we get from the balanced equation. So this term here has a temperature that changes, right? I'm going to scroll up. The temperature is changing by 1.640 degrees. But this term here, we're assuming that this reaction occurs at 298 Kelvin. So we're assuming a constant temperature in here. So this is based on the balanced equation, kind of like a theoretical amount that we're plugging in, assuming it's an ideal gas. So if that's the case, we look at this balanced equation. We have 12 moles of gas that we're producing for every 12 moles of gas that react. So that's just 12 moles minus 12 moles. The gas constant is 8.314 joules per mole degrees Celsius. And the temperature, or Kelvin, we could put Kelvin here. Actually, we have to put Kelvin because this isn't a change in temperature. It's the straight up temperature, 298 Kelvin. So Kelvin cancels out, moles cancel out, and we're left with joules, but it's not just straight joules, right? Oh, I don't. What's 12 minus 12? 0. So this is 0 joules. Now, it's okay here. Now, this term is just totally drops out. But if this is not 0, then this number is going to be per mole of sucrose, because these change in moles is based on the balanced equation. And the balanced equation looks at if 1 mole of sucrose reacts with 12 moles of oxygen to produce 12 moles of CO2 and 11 moles of water. So for this reaction to occur, this delta PV term would be per 1 mole of sucrose. So you would plug this number in as what per 1 mole of sucrose. And our internal energy is, where is it? It's right here. This is per mole of sucrose as well, negative 13,629.6. So negative, I'll put it in blue, negative 1392, is it 929.6? Yep, 929.6 kilojoules per mole. Great. And lastly, we will check for significant figures. We have 4 here in the molar mass, but I think there's less here. 1, 2, 3. Oh no, there's 4. Where did this number come from? Negative 24. That's the C-cal. So that's 1, 2, 3, 4. We have 5 here for some reason. 1, 2, 3, 4. Oh, this has 5 sig figs. 1, 2, 3, 4, 5. This has 4 sig figs. And this number came from here where we have 5, 5 and 4. Okay, so this one has 4 sig figs. Calorimeter. And that means this has 4 sig figs. I should have carried this throughout. This would have made life a little bit easier. This is 4, 1, 2, 3, 4. That's 4 there, and then it's 1, 2, 3, 4. So we have 4 sig figs. Okay, 4 significant figures. So our final answer is negative 13930 kilojoules per mole. Right arm. Okay, hope you appreciated that. Hope you got some benefit from this, and thanks for watching. Let me know if you have any questions on it, and I'll see you in the next video. Cheers.